So how much do you know about a simple harmonic motion?
Not much.
No?
Not
Oh,
much.
I think you have to study the did your teacher show you that the oscillation of the spring or is object of the spring, can you see?
Mm-hmm.
And imagine this is spring, can you see? In that elastic spring, what would happen if you push it down and let it go? What would happen?
It would bounce back.
It bounce back. Do this stop?
It would keep bouncing
It
until
keep
it stopped.
dancing. You keep bouncing. Can you see? So that is if we use this is vertical axis, we can use either x or y, up to you, right?
Mm-hmm.
You can use y because vertical, that is the original position. Okay, this called so if you put it downward and without any velocity, then that would be the negative amplitude. Okay, the maximum velocity would be equal to a relative to the origin. You see, so
Yeah.
this is mass n. So if you just keep watching, if you just monitor this height as a function of time, so you will see that if you just do another formula, to another diagram here, if you just take the record, okay, this vertical is y, that is the position of the object m, and this time it is a time axis, all right?
Mm-hmm.
So that would be that is y, that would be 0, that would be our maximum displacement on both sides. Okay, a is amplitude. So if you go to the time t here, if you divide this into 4 equal interval, if in this case it's starting from the bottom, right? If it doesn't matter, we can assume this starting from the origin. Then that would be the exactly sine function. Can you see? Can you see that?
Mm-hmm.
Of course, they will continue, right? They will continue. This is exact one. This is the whole period. Can you see? This is t. This is half t. Can you see?
Yeah.
Quarter t. T is a total period. Can you see? Now, can you write the formula for y in this case? Or you can write the formula here, up to you. So this is a mass. This is example of the mass on spring. Yeah, you can incorporate the t. No, that's not the case. Think again. Doesn't matter. You keep thinking. What would be that in mass in the mass? We use this b. Do you remember? We don't use t. We use b. Do you agree?
Mm-hmm.
We use the b and x. Okay. So what is the relation between b and the period? So this is not right.
Oh, 2 pi of
Exactly. So where b is equal to, can you see? 2 pi over capital T, can you see?
Yeah.
Alternatively, in physics, this is in math, okay? If we in math, in physics, we prefer to use this Greek letter called omega. Can you see? Use this formula. Can you see? It doesn't matter. So you can either use bx or you can use wt because our time. This is time dependent. Can you see? So maybe we can just write the formula here. This is a equal to sine omega t. All right. And because omega is in the same position as b, so therefore omega is simply equal to 2 pi, actually 2 pi frequency first, all right? And also equal to 2 pi t. Can you see? Where we have used this simple relation that the frequency is a reciprocal of period. Can you see? So in physics, we prefer to use omega. So omega is called angular frequency because it's proportional to frequency, right? So it's called angular You don't have to know this, but you don't have to. Just remind you. You don't have to remember this. It's called angular frequency. That is the name we refer. When you study the wave in physics, this became very important. Okay. So the omega is proportional to f, different by 2 pi. Okay.
Yeah.
That is so we just this is mathematical notation, right? So they just use capital B, but in physics we prefer to use omega. That's all. Now that is simple harmonic motion. Can you see? So in other words, the position. So the position. So the position. Position of the object. Position at any time can be written as y as a function of time equal to a sine. You can use cosine, up to you, right? You can use sine, you can use cosine, doesn't matter. Sine omega t, okay? So this kind of periodic motion, so obviously is a periodic motion, right? So this is a periodic motion. So this from this one, we know that this motion is a periodic motion. Okay, periodic. Okay. Now, this would be the first equation for the position. It's called the simple harmonic motion. Okay. So that is this motion is this motion can you say move downward up repeatedly. It's called a simple harmonic motion. Simple because we can use a sine function. All right. It's called a simple harmonic motion. Harmonic motion, or SS motion, or simply called SHM. That's definition. All right. Now, if we use a definition in physics, how about the velocity? Because this object is moving. Okay. Can you work out the velocity?
Frequency times lambda.
Now, what is velocity? No. Oh, don't be careful. Don't you confuse with the wave? Are you talking about the wave equal to lambda frequency, right? This is for the wave, not for the say. This is for the wave. That has nothing to do with simple harmonic motion. Simple harmonic motion is oscillation. You see, oscillation. So in your ATAR textbook, they didn't teach a student what is oscillation. They jump to the wave. All right. That's why I'm not surprising you would pick up this velocity formula. This oscillation can be sum of velocity in a special case that becomes simple harmonic motion. Okay. For example, if you have the oscillation like this, can we draw some? If you draw something like that. So this is a very this is just an example of oscillation. Can you see? Y as a function of time. If the oscillation is like this, so this is more complicated. So this can you see? Like this, can you see? Can you see that? So this is oscillation. Maybe it's periodical, but certainly it is not simple, right? It's not as simple as a sine function, all right? And just give you extension. This complicated, in this case, this y, I'll give you some ideas. So this y, this oscillation, right, can be subdivided into different sine function. Can you see? I sine omega I and t. I from 0 to infinity. Does that make sense?
Yeah.
In other words, a complicated oscillation can be subdivided into simple harmonic. Can you see? This is a simple harmonic. Can you see?
Mm-hmm.
So if you plus them together, if you add them up, then of course there are more than 3 components. Okay. If you add them up, then you will get this original oscillation. You know what I mean?
Mm-hmm.
So any complicated, no matter how complicated the oscillation is, we can always use a simple harmonic motion to describe it. All right.
Mm-hmm.
Now, when we work out the velocity, we really have to use our definition in physics. Can you see this is general definition? Can you see the first derivative? Can you work it out? That is the definition, because the velocity is not constant. By the way, this formula means that V is constant. Can you see? V is a constant. But in our case, our velocity, the velocity in simple harmonic motion is not constant. Do you agree? It's changed periodically. Good. How about the third important quantity is called acceleration? By definition, acceleration. How can we work out a formula for acceleration? V, yeah, you can go. A equal to this, yes.
2.
Good.
Mm-hmm.
So I have 3 formulas, do you agree?
Yeah.
1, 2, and 3. Now, let's go further. Can we do some substitution? If we substitute equation 1, if you just substitute equation 1 into equation 3, what can we obtain? By just simply do some substitution. So what is A? Basically, what is A? Oh yeah, go on. Yes. A is equal to this, right?
Yeah.
So that is a general. This is criteria to argue whether the oscillation is a simple harmonic motion or not. Can you see?
Mm-hmm.
And some textbook use X. It's the same. If they prefer use X, that would be the formula in your textbook. Can you see?
Yeah.
So this is a criteria for whether the oscillation is simple harmonic or not.
Mm-hmm.
Okay.
Yeah.
That's it. That's answer your question. What is a simple harmonic motion?
Yeah.
So this is you can call this the fourth formula if you wish. Do you have any problem solving associated with this simple harmonic motion?
Yeah, I do.
Okay, let's go to next page. So you can always go back to this first page, all right?
Mm-hmm. So the question is, an object with a mass of 2 kilograms.
Yes, can you write down? Can you write the mass given? What is the question 1? Can you write the condition given? So we just simplify that question by mass equal to what? 2 kilogram. Can you see?
Mm-hmm.
Can you do that? You just copy that condition into this simple form. Equilibrium. Yeah, at t equal to 0. Okay. So which means which means y0, can you see y0 equal to 0? Do you agree?
Mm-hmm.
Okay. This is the same, so this is equivalent. These two statement is the same. Period is given, amplitude is given. Amplitude is a centimeter, millimeter, or any unit?
Oh, it was seconds.
Yeah.
This is meters.
Meters, okay. Oh, good, that's why, that's international unit system, okay. So what is after?
It says determine the expression for the displacement.
Okay, displacement. So y, yeah, by the way, the position is also called a displacement because that is a change from relative from the origin, can you see? Our formula y is always equal to the displacement, can you see? Because we count from the origin, so this is called a displacement. Displacement, oops. Oh, one moment. Okay. Displacement. Okay, can we write y if we know this condition? So what is the formula we use for y? We obtained in the previous page.
Oh.
Yeah, that's it. So what is omega? That's right. Okay. Can we substitute this number into this formula? Then we will get the formula for displacement. As simple as that. Okay. Finally, what is yt? Yes. Good. Define sine. Yes. Okay.
Yeah.
It's simple. Yes. Nothing to do with math. Can you see?
Yeah.
This formula has nothing to do with math. Oh, of course it does, because if you want to ask phasor, what is the relation between t and m, then you will encounter this question. All right. Is that a mass or spring, or is the pendulum? What type of this? Can you read the question?
It's a vertical spring with a mass, and then it says determine the stiffness constant of the spring.
Yeah, have you done that? The second question, right? So that is obviously this is the same scenario. You can consider that is the displacement is let's draw a diagram here. Yes. So you can consider this is a spring with elastic constant k, right? Or stiffness constant. They call it sometimes called elastic constant, sometimes called a stiffness constant, with a mass top m at the bottom. Can you see? Good. So how can we work out the relation between t and the elastic constant or stiffness constant? So this is the first part of the question, right? So second part is what is the relation between t and k, right?
Yeah.
Okay. So I give you, because this topic should be taught in physics. So therefore, I give you a hint. How can we use Newton's second law to build equation? According to Newton's second law, what can we say? What can we obtain?
Force equals mass times acceleration.
Yes. Yeah. So we have force. So what is you have another law is a F is equal to ma, right? But in the meantime, the force in this case is equal to the constant multiply the displacement. In this case, the y, you see? So that is equilibrium. This is equilibrium position if we use y. So these are y-axis. You can use x, doesn't matter. Okay, you can use y. So the y will be the displacement. For example, if you put object there, elongate that will be the position. Can you see?
Mm-hmm.
And otherwise, if you compress that, or you compress that, that is their position. So that is the two formulas. If you combine these two formulas, we got what? The force is negative, always negative to the direction of y-axis. This is called Hooke's law. So did they tell you this Hooke's law?
No.
Hooke's law. Okay. If you combine these two formulas, what is the formula for the A, by the way?
M over F.
Yeah,
Oh no,
right?
F over F.
You get negative, right? Negative sign here. M. Yeah, what is F? Can we combine these two formulas? If you that case, the first is positive here and negative. So if we just rearrange that one, A can be written as a constant, can you see? K over M multiplies Y, all right? So if you just compare with the definition we just derived, A equal to omega square Y. So what is omega?
2 pi over T.
Square root. No, 2 pi over T. No. No, here you just compare these two. Because we're looking for the, can you see?
Omega equals square root
this
of K
must be
over F.
identical, can you see? These two quantity must be identical. That is how to determine the period. Can you solve the formula? Can you work out the period? Or can we just, can you solve this? Can you solve this? Can we find the what is omega and then what is the T? Can you find these two formula?
Oh.
Uh-oh.
Omega.
No, you miss out this. Can you see? We have two equations. Okay, be careful. We have two equations. This is equation. Another is equation. Okay. Yes, root K over M. Can you see? If that's so, then we can use the relation between omega. Yeah. Can you go further? Can you go further for period? Okay. And if you go further, we can rearrange that as a root Km, M over K. Do you agree?
Yes.
This is a very important formula. Okay, for the spring, for the oscillation of this of the.
How do we get M over K?
Oh, we just rearrange that. That's in algebra. Did you see that? So we have 1 over root K over M, right? So if you just multiply square root M on both numerator and denominator, then we can cancel this M, can you see? After that, we got root M over root K, can you see? And that's why we can derive this formula. Okay, this is just algebra, can you see? Algebra.
Yeah.
Okay, not almost, yeah, you almost derive this formula. Very good.
Yeah. Okay. Now just and to get the How do we know what K is?
A K should be given provided. Because in this time, they are looking for K, right? We just use this formula to solve the K. Can we solve the K? Can we use this to solve the K? Just rearrange that. What is the formula for K? This is the formula for T. No, it's square. You have squares in because you have first square both sides. T square. How about 2 pi? 2 pi must be square. Yes, that's correct. So this idea, the subject from physics, right? It should be properly learned when you start, before you start the wave, you understand?
Yeah.
Before you start the wave, we should really learn this part, simple harmonic motion. But because they want to be taught, they want to teach you this in mathematics, so therefore they didn't teach you this anyway. What's the next question?
Determine the velocity after 1/6 seconds in terms of t.
Yes, this is part of question, right? So we got a formula, and we just continue here. So there's a third part. Can you try to solve this part in the middle? There's a third part of the question, right? Yeah, we should have a lot of space here. Can we solve this? So what is given? Time given? Oh, 1/6, simple. Yeah. It's a spatial angle, isn't it? It's a spatial angle for sine 6 degree, 60 degree. Okay, what is sine 6 degree? Can you use a triangle to work out the 6 degree sine?
Square 3 pi 0.05 times.
Yeah, so you have use you have draw the equilateral triangle, you see? Equilateral triangle, they got this internal angle equal to 6 degree. If you added another height here, and then we choose each side is 2, right? So that be 1, this is 6 degree. There's a pi over 3. This should be root 3. You agree?
Yeah.
Oh, well done. Well done. Okay. That's it. That's it.
Yeah.
Got everything. We save this page. Oh, let's go to next page. That's all. Any question? More question?
Yes, I had some questions about Gaussian elimination.
Can you write it down? Gaussian elimination. Which context? Are you starting matrix or?
Yeah.
Yeah.
And vectors.
Yeah, that's totally different subject. Are you starting in 2 by 2 or any 3 by 3 now?
3 by 3.
3 by 3. Yeah, there's Gaussian cosine, right? It's Gaussian, not cosine. Gaussian, right? It's Gaussian.
Yeah.
It's Gaussian. Row elimination, right? Row elimination. Yes, that is a method, elimination. Oops, sorry. Yeah, that is how to we dealing with matrix. Can you give an example? I show you. You write the 3 by 3 matrix. I show you how to do that.
I think any 3 by 3 matrices work, right?
You can write. Then you can write the 3 by 3 matrix. I show you how to manipulate that matrix. Yeah, you can 1, 2, 3, 4, 5. Yeah. Okay. Okay. Oh, you put them together, right? You put them together. Coefficient. This is coefficient. So basically, my understanding, you are dealing with this question, right? You are dealing 1, 2, 3, 3, negative 2, 3, and 2, 4, 6, right? And multiply, say x, y, z, and equal to 4, 5. Is k? Is this k?
Yeah,
K is
because we have to
unknown.
solve for k.
You have to solve the k. What is the original question? You have to find the k, or you want to find x, y, z?
We want to find k.
What is the equation to find ak? So what is the original question? You see, you are this question contain many components, right? If you just want to know what is the Gaussian rule elimination, I can show you. However, here you are dealing with simultaneous equation. Yeah, I can see. That's exactly. So work out the k, right? Equal to k. Okay. Yes, actually, these two are equivalent. Can you see? This is a simultaneous linear equation. This is in its matrix form. Okay. And if the object, if subject is a k, well, you have only two variables. Oh, this is z. Is this z or 2? Z, right?
Yeah.
Okay. Okay. Now, what is the question? We should be able to find the x, y, z, or should we find just k? What is the question? Can you show me the question?
We just have to find k.
We found it. No, it doesn't make sense. Okay.
Because this is a 3D plane.
Sorry.
This is the same.
Can we show you screen? Let's read. Let's look at the original question. Yeah.
It's in a book, but I'll show you if you go back to whiteboard.
Yeah, one moment. Yes, I can. You want to share your book, a digital book?
No, it's a physical book. But it's a vector thing.
Look, this is a separate issue, all right? We cannot, this question so far is incomplete. I can show you what is the Gaussian's rule elimination method. Now, there are many, you can use this method to solve a variety of questions. All right? However, if that is you see, in this question, can we return to your question? So you can't, in general, we are not introduce additional variable. We just introduce, can we call this is 7, all right? Can we call this 7? If that is the case, before you go, can we just show you, in this case, we can solve x and y, z, or a vector, can you see? X, y, z. We just assume this is not the case, it's just 7, all right? Then we can just find the inverse of this matrix, can you see? So that is how we, this is 4, 5, 7. In this, if that is objective, if that is a question, then we can use all Gaussian role elimination by diagonalize, can you see? Make this matrix diagonal. So that is objective, can you see? The Gaussian law allowed you to manipulate a matrix. So get this at diagonal, you see? In other words, all other off-diagonal elements must be 0. So that is a question. That is a question. Yeah. That is one way I can show you what is Gaussian rule elimination method. However, of course, Gaussian elimination method can be used in other cases, such as probably in your case. Can you continue? So basically, can we just use a graph to indicate the question, all right? So basically, we have two vectors in the 3D diagram. Because we have so basically we have the we have this 3D diagram. It's called X and Y, Z, eh? X, Y, and Z. And we know the point can call it P, and his coordinate is X, Y, and Z, all right? And that vector, we can use a vector to display that. So that's one vector, can you see? That is represented by these single column matrices. And in the meantime, we have the another vector whose x, y is 5 and 4 and 5 respectively. So this is 4 and 5, and roughly can you see the 4. This is x is 4, y is 5. Can you see? X directing. Can you see? So this is called Q. Can you see? This position is this just this 3D. So this is x. Can you see? This is x equal to 4, y equal to 5, but z number, z coordinates is undetermined. But we know that these would be just represent the vertical straight line. Do you agree?
Yeah.
Okay. So that is my interpretation of your question. Can you see? So this blue color, the straight vertical straight line can be called. So that is any position. I mean, just draw any position. I draw the another. Let's use a red color. So if we just pick up any position of this position, can you see? Any position, can you see that? Can you see just this is any position? This position is called PQ, because it's called Q, can you see? So this is just one of position. So this is called Q, can you see? This position, whose coordinate can be written as 4, 5. Oh, use your notation. 4, 5, K, right? Depends. So in this case, K is larger than. So basically, any in this part, K is under this plane. K is negative, right? But above that, K is a positive number. All right. So that is depend on whether it's under or above this XY plane. Okay. So that's what I can say. So so basically this we have two. We have then they have a simple transformation. Okay, they will transform this P vector to this vector, and this transformation is called A. Do you agree? So this is the A matrix. This is A. Can you see? So that is what I can draw based on the information you have. Now, they must have some condition to determine, to give the exactly what K is, all right? Any other condition? Can you read the question? What any other condition? Otherwise, it's undefined, can you see? Because if you don't give the K, and how can we know this, how can, or otherwise, can they give X, Y, Z? Did they give, can you double check, did they give X, Y, Z or not?
XYZ is 2, 4, 6.
Oh, yes. Oh, that's why. You have to really ask the right. If you just right here, can you see? You see that become clear, right? So given in this case, we have the condition given that X, Y, Z vector, the P, the position P, the coordinate, right? Can you write it down? What is the number here? Can you write the 3 number here?
Oh wait, I think that's just a bad question. Wait.
No, you just tell me the 3 number. Did you just tell me 3 number for X, Y, Z for point P?
They haven't actually given the 3 numbers.
They didn't. But how can we solve? How do we solve this question?
They say use a Gaussian technique to determine the value of K, for which there are infinite solutions.
Well, in physics, so basically K is control of this linear function, right? So that is right question. So for what the K, for what is the K value that gives an infinity number of solution, right? So just without, what do you think? Is K should be equal to 0?
What would K equals 0 give?
Yeah, it can. Yeah, go to your question. This is complete question. So in your case, you got the X. This is last one. I just rewrite this as a K. All right. I rewrite this as a K, which is obviously that's where. Yeah, that's right. You are talking about some criterion or method which can be used by just choosing the K. Then we know without solving the equation, without solving these simultaneous equations, we should be able to know that if there are any infinity number of solutions, right? So this is a question about that whether this I'll put it another way, these all represent a straight line. Can you see? Do they?
Yeah.
So or plane? Sorry, that's straight plane. Do you agree? You can also consider spring. So they are just asking whether, I know if you go to that, so whether you have this scenario, and if this two plane or three plane rather. Is one plane, the second plane, is third plane. Can you see? So this plane you can draw in the space. Well, we can see that. So these three planes were in general they were intercept. Can you see? And this, in general they were intercept. Can you see for this green one? Okay. There will be intercept in this case. In that, if that is so, that will be their solution of two equations, all right? If the third equation is, let's just draw several scenarios. If third, this is will be origin color. If the third square, if the third plane is in that case, can you see? In that case, so so that is the third plane. Can you see this diagram? So in that case, you will see another interception. Can you see? In this way, they will have unique solution for X, Y, and Z. Do you agree?
Yeah.
So that is a unique, a single or unique, a single or one solution. And there's one solution. Can you see? Solution. We just use a graphic to illustrate what is the question, what is the problem. All right. However, if the what will be the infinity? These have only one solution, say one. How can we get infinity number solution? What would be the scenario graphically?
If they don't meet?
They don't meet at all. There's no solution. No, that means no solution. It's different. There's no solution. No solution. One is no solution. Okay. So there's no solution. So this is one scenario. Can we call this is a scenario one? Can you see? Second is have one solution. It's different idea. Can you see?
Yeah.
And then third scenario is had infinity number of the solution. So the criterion you mentioned will be used to determine which would be the case for the K, right? That we were landed in this scenario. Do you agree?
Yeah.
Now, in my understanding, if the third equation is parallel to any of these plane, then we should have infinity number of solutions. Can we just draw this diagram, this graphic first? Can you see? If we have the origin, I use their idea. I use the origin color first. Okay, if this hypothetically this is the first plane, all right. And the second plane is, I still draw that second plane. So second plane is have the intersect with the first one. Can you see? So in this case, these have intersection. They have straight line. Can you see? Can you see they have straight line? That is the intersection. Many of them, right? Now, if the third equation, that is criteria now. So if the third equation, a third plane, sorry, if the third plane is parallel to say the first one or second one, doesn't matter. We just assume if the second plane is parallel to the first one, so we got this scenario. Can you see? In this case, we should have infinity number of solutions. Do you agree? Because all of these will be our solution. Do you agree? Unlike this one, they only have one. Can you see? They can only have one, but here they got infinity number. Okay, so this is so therefore, how can we make these two? How can we make these two parallel to the you can choose one. That makes sense. Without invoke any particular method, we can argue that if k is equal to some, can you see this is a proportional? By the way, this will determine the direction of the plane. Can we do you remember that when we started the this is their color? Can we use the green? Can you see the green? So if this is green plane, right? And therefore the directional vector, do you remember directional vector? Directional vector, which will be perpendicular to this plane, okay? And this vector will be equal to these three numbers. Can you see? So this vector, this directional vector, will equal to these three numbers. Can you see? 3, -2, and 3. Do you agree? Of course, if you want to get a unit vector, you have divided this module. Okay. So it now is clear, and there's if you just compare these three formula, and the third one, by the way, that is a direction. So we just have to manage this coefficient to see if we can get to this. I can see this chance. We can manipulate. We can make this happen. If you pay attention to the first plane here, can you see? And the last one. What is similarity between these two? Can you compare in terms of their directional vector? In terms of their directional vector. They are the same. Okay. The direction vector of the first and third one are the same. Do you agree? Can you see? Except this is just doubled. Can you see? So what would happen? So if you just multiply, if you just multiply 2 for the first equation, we would obtain the 2x plus 4y plus 6z equal to 8. All right. So without invoke any method, we can argue that when k equal to 8, can you see? When k equal to 8, and we will end up with this scenario, infinity. In other words, not only the parallel, but they actually overlap. Can you see?
Mm-hmm.
So in the special case, I'm in the special case. Probably these actually they are actually exactly not just parallel, but overlap. Can you see?
Mm-hmm.
So this is so this is k is not equal to 8. All right, but in this case, k is equal to 8. Yes. So I just correct my description. In order to get infinity solutions, two of the plane must be on the same plane. Does that make sense? So that is your answer for K. Of course, this is just use graphical analysis, all right? We not just graphic, we just is the idea. This called this N is called the directional. Can you see? It's called the direction. Do you remember the directional vector? Last year?
No.
We started application of the vector, probably a long time ago. We use a small n. Do you agree? Now let's just go to the method. Can we invoke that method now? If we know the objective, all right? So basically, we know that if you just we just multiply, and we just multiply. For example, if we multiply, let's just talk about. So if we multiply 2 of row 1, okay, and row 1, and take row 3. I'm using Gaussian method now. Can you see Gaussian row elimination method in 3? So you know what I'm doing now. So basically, this is our. I use same coloring. So this is our. These are the row 1. Can you see? You agree? This color means R1, right?
Yeah.
And the red coloring, these will represent R3, row 3. Do you agree? So according to Gaussian elimination method, we can change the row by multiply a constant or add or minus another row, and the whole relation, a whole matrix doesn't change. You know what I mean? However, we have objective to get rid of this third row, okay? As a result, you tell me what would be the new matrix now? Can you write this? So nothing changed to row 1. Can you see? 1, 2, 3, nothing changed. Nothing changed to row 2. Do you agree? 3,
Yeah.
like 2, 3, and nothing changed to this part, 4, 5. But something will happen to the row 3. So what is the consequences? Yes, that's it. Can you see?
Yeah.
So that is another way, use the Gaussian row method to determine what is the K. Can you see? So K must equal to 0, it's equal to 8 in order to satisfy the condition, right?
Yeah.
Wow, that is totally different topic from previous question.
Yeah.
Simple harmonic motion, you jump to the Gaussian row elimination method to determine the condition under which there's an infinity number of solutions. Just remind you, okay, these 3 scenarios are quite different, all right? Graphically and geometrically. So basically, so if you just rewrite this coefficient, they may spend more time on this question. It's a very typical question. If I just spend more time to rewrite this as simultaneous question, what can we obtain? I use this. Can use this space for you. Can you reconstruct the same simultaneous question based on this result? You know, can you just make this question clear? Because 1, 2, 3, 3, -1, 3, and 0, 0, 0, and that is 4, 5, k take 8. Okay.
Mm-hmm.
Can you construct the simultaneous equation based on this notation, based on this matrix form? Yes, first equation, yes. Or you can use ABC, you can use X, Y, Z, it's okay. So the third equation is k equal to 8, isn't it?
Mm-hmm.
The reason, so this is algebraic, yeah, that is algebraical. So today we use a two approach, right? We use a graphical approach. We can also use the algebraical approach. So basically, in other words, so this is called a simultaneous linear equation, right?
Mm-hmm.
If you have 3 variables, but you have 2 independent equations, so that would be the scenario. Can you see? If you have, in your case, A, B, C, you can also use X, Y, Z. If you have X, Y, and Z, right? But you only have 2 equations. Can you see? 2 independent equations. So this case, so in this case, these are 3 independent. Can you see? Independent linear equation. Independent. Oops. And let's finish this writing. Independent linear equation. Can you see? In that case, you have unique solution. Can you see? You have unique solution if the 3 equations are independent. Okay. Of course, there are other constraints. Another constraint is inverse must not equal to 0. Okay. Another constraint is that the inverse, not inverse. The what do you call it? Determinant. Okay. Determinant is not equal to 0. That is another constraint. All right. It's called the determinant. Do you remember? Determinant. Okay. So if 3 linear equations are independent, plus their coefficient matrix whose inverse, whose determinant is not equal to 0, then we have only solution. Okay. However, in our case, in any case, if you have less than 3 independent equations, including 1 or 2 independent equations, then the solution will be infinity. Okay.
Yeah.
If, however, both the plane have not is parallel. Okay. There's no intersection in this case, right? That in this case, then you should have no equation. Do you understand? Graphically, if they are parallel, there's no intersection at all. Can you see?
Yeah.
That makes sense now. Wow, we have a long journey from the Venus to Mars today.
Yeah.
All right. Okay, let's leave that. Okay, see you next time.
Okay. Thank you. I'll see you next week.
Goodbye.
Bye.
Bye.